Hey guys, welcome to Safi Mixed. In this video, I will talk about the concept and discovery of trigonometric functions. Since the mother to trigonometric function is right triangle, therefore I would like to begin from the geometry of right triangle. And to this end, I first draw a horizontal line which I represent with OA, and then I take another line OB which is making an angle theta with line OA. That is, the angle at vertex O is theta. Then I consider a point which I represent with P and drop a perpendicular from point P on line OA. And the point at which it touches line OA I represent with Q, then the angle at point Q is 90 degree. So we in fact have a right triangle OQP, which for further visibility I shade it with blue color. Now the base of this triangle is OQ, the perpendicular is QP, and the hypotenuse of this triangle is OP. If I represent the side lengths with A, B, and C, that is, base has a length A, perpendicular has a length B, and the hypotenuse is of length C, and I want to construct ratios of these side lengths, and I begin from the ratio of perpendicular to hypotenuse, that is B by C. Since the hypotenuse of right angle triangle is always greater in magnitude to the magnitude of perpendicular and base, therefore B by C is a real number which I represent with K and is always lesser than 1. Now, if I take another point which I represent with P prime and I repeat the same procedure, that is, I drop a perpendicular on line OA which meets at point Q prime. Now we have another right triangle OQ prime P prime which I shade here with a light green color, and let the side lengths of this right angle triangle I represent with A prime, B prime, and then C prime, and I want to construct the ratio of this prime triangle for the perpendicular and hypotenuse, that is, I construct B prime over C prime. Now the most interesting thing is that this ratio is always equal to the same number K. This in turn means that the ratio of the perpendicular to hypotenuse of the prime triangle is exactly equal to the ratio of perpendicular and hypotenuse of the unprimed triangle. This is very interesting and you should pay your attention to this. This equation tells that the value of the ratio of perpendicular and hypotenuse for these two lines, that is A and B, is completely independent from the choice of point P prime or any other point along this line. And this is a very interesting property. Similarly, if I take the ratio of base to the hypotenuse of the unprimed triangle, then this ratio is exactly equal to the ratio of the base to the hypotenuse of the prime triangle. And again, the length of the hypotenuse is always greater than the length of the base. Therefore, these ratios equals to a real number m which is lesser than 1. However, this M may or may not be different from K. For certain configurations, M and K may be equal, but in this case, we consider them different. And now, if I take the ratio between perpendicular and hypotenuse, I can write B by A, that is perpendicular to the base of unprimed triangle, is always equal to the ratio of the perpendicular to the base of the prime triangle, and this is always equal to a number n. This time the number n may be greater or lesser than 1. are maybe equal to or maybe exactly equal to 1. So there is no strong restriction on the value of n. This means that the ratios of the different sides of the triangles are completely independent from the choice of the point on line B or from the choice of point Q, Q prime, etc. on line A. So far as we are not changing this angle, these ratios remains same. On the other hand, if I consider another line OD which is making an angle phi greater than theta, or in other words different than theta, it may be smaller than theta, but in this case I consider phi is greater than theta, and I repeat the same procedure, that is I choose a point on line OD which I represent here with P double prime, and I drop a perpendicular on line OA, then uh, I represent the point with Q double prime, and this in fact is 90 degree. Now we have a third triangle OQ double prime P double prime, which is a right triangle, and for greater visibility I shade this with this light black color. Now if I represent the side lengths with A double prime, B double prime, and C double prime, and construct the ratios like I did before, then I can write for this triangle the ratio of the perpendicular B double prime to C double prime equals K prime. Note this thing. The ratio of the double prime triangle of the perpendicular to hypotenuse I am representing with K prime, and this K prime must be different from this K, which means that this ratio is not equal to the ratio B by C of the single prime triangle or of the unprimed triangle. Note this is very important. When we change the angle at vertex O, then the value of this ratio becomes different from the previous one. Similarly, if I take the ratio of the base to the hypotenuse of the double prime triangle, then it equals to a real number m prime, which again is different from the real number m. And this, when it is different from the real number m, that means it is not equal to the ratio of AC, that is not equal to this equation. And similarly, if I construct the ratio of the perpendicular to the base of this double prime triangle, I get a number n prime, different from number n. So that means this ratio, that is b double prime divided by a double prime, is not equal to b by a, or not equal to this one equation. So this is in fact very interesting for the ratios of the sides of triangles which have different angles at the vertex O. Now, if you are critical enough, you must have noted that the ratios of the sides of triangles are in fact functions of the angle at the vertex O, and are independent from the choice of points over the line OB or OD. So this property of the ratios of the sides of a triangle in general lead us to define functions in the form b by c. Now note that I have used different colors, which means that I'm generalizing the equations of the ratios of triangles. So b could be the base of any triangle, and similarly c is a general hypotenuse. Then I can write b by c as a function of theta, and I represent that function with f. Similarly, the ratio of the base to the hypotenuse is also a function of theta, and I represent that function with g. And lastly, I represent the ratio b by a, that is the ratio of perpendicular to the base, equals h of theta, that is all the three ratios are functions of theta. Now, the founders of trigonometry prefer to prefer not to use functions like f, g, and h. Rather, they specified the names of these functions and wrote for f function as sine of the angle. And for g function, they prefer to write cosine of the angle. And for the h function, they wrote tangent of the angle, which are abbreviated as sine, cos, and tangent. So the trigonometric functions sine, cos, and tangent are in fact the functions which describes the ratios of the different sides of a right triangle. And specifically, the sine function describes the ratio of perpendicular to the base. The cos function describes the ratio of base to hypotenuse, and the tangent function describes the ratio of perpendicular to the base. Now, in addition to these three functions, we can reverse the ratios. That is, instead of b by c, I can take c by b, and a by c, I can take c by a, and similarly, I can invert this ratio to a over b. With this approach, three other trigonometric functions are defined in terms of the inverse of these functions, and the first one is cosecant theta. That is, cosecant function is the inverse of sine function. And we have another function, secant function, which is the inverse of cos function. And lastly, cotangent function is the inverse of tangent function. These six functions complete the set of trigonometric functions, and these functions can completely be represented as the ratios of the different sides of a right angle triangle. At the end, if you haven't yet subscribed to Safi Max, kindly support the channel by pressing the subscribe button, and don't forget to hit the like button on the video. Thanks for watching.